Okay, good morning. So, this is our 26th lecture of the course Compressible Flow and Gas Dynamics. In the previous lecture, we have discussed some of the intricate issues regarding the nozzles, and then we also performed two numerical problems. And in the second numerical problem, we saw that there was one nozzle, and then at the at some section at the nozzle, actually it was given that shock wave, a normal shock wave has formed. Okay, so this is the part of our second problem where normal shock wave was given, and its location was specified in terms of, say, if this is my area of throat, if this is the area at the occurrence of the normal shock wave. So it was given that A by AT is known to us. So if A by AT is known to us, it means that location of shock wave is actually known to us. Okay, so location of shock wave was known, but this is something which will not be actually always possible. Okay, so if you see, for a particular nozzle we will be able to know only three parameters. First is pressure which we are maintaining at the reservoir, then exit pressure of the nozzle EE, and then we will be also having this area known AE, exit area of the nozzle, and then area of the throat. Okay, so these are the only parameters which will be known to us. If these are the parameters known to us, and then we have to check that where shock wave is actually occurring. Okay, so this is something which is a problem now we have in hand, how to determine the location of the shock wave. Okay, so one simple approach can be that arbitrarily, so say approach 1, I am writing it. So approach 1 is basically iterative procedure. Okay, so in case of iterative procedure, what one has to do, one has to first assume. Okay, let us assume that I have some ratio of A by AT, and we are assuming that at this ratio of A by AT, actually our NS is present, normal shock wave is present. Okay, so we have assumed. Once we have assumed, then we will do all the analysis which we have done in problem number 2 of previous lecture. Okay, so in the previous lecture we have one problem number 2 where the location of the shock wave was known to us. So if I am assuming A by AT, it means I am assuming that location of the shock wave is actually known to me prior. Okay, so now I can perform all the analysis which I have done in problem number 2, and then I can determine the ratio of PE by PO. So this is the ratio which I have calculated, and then 1 PE by PO is known to me. Okay, so 1 PE by PO is known to me. So I can check, make the comparison of this known and unknown parameters, and depending upon that I have to all the time adjust this value of A by AT till the calculated value of PE by PO is matching with the known value of PE by PO. Is this point clear? So this is approach 1 where we have to follow the iterative procedure. Now, being an iterative procedure, it is depending completely upon the initial guess, and if your initial guess is too much away from the actual value, then in that case you have to follow too much of iterations. Okay, so there is one more approach, uh, and that is your approach number 2, and that gives actually a more deterministic situation where actually we can predict directly the first location of the normal shock wave, and once we have predicted, then we can follow the remaining procedure. Okay, so in this case, if you see, typically for a nozzle I can determine that mass flow rate of the nozzle will be nothing but P naught into A star, sorry, considering the throat properties, I can determine mass flow rate is, say, considering the properties known at the throat. So rho star, A star, and V star. Okay, So I can even write this rho star A star and small a star. Okay, considering that at this Mach number V star will be equal to A star. Okay, now we know that normal shock wave will come only when we are having actually choked flow situation. Okay, because ultimately what happens in case of choked flow situation, our pressures are in between the pressure which is required for isentropic subsonic supersonic flow and complete isentropic subsonic flow. So in between two, whenever I will be having pressure, that is nothing but the situation of a choked flow. So subsonically it is a situation of choked flow, and corresponding to that choked flow situation, we will be finding that we will be having nothing but occurrence of a normal shock wave. Okay, so for a choked flow situation, for a choked flow situation, if you do slight manipulation of these parameters, you will be able to predict that mass flow rate will become P naught into A star divided by square root of T naught times square root of gamma by R into 2 divided by gamma plus 1 whole power gamma plus 1 by gamma minus 1. Okay, so this is the value of mass flow rate which one can determine for a choked flow situation. Okay, by doing some algebraic manipulations. So if you see in this situation, what we have is m dot is equal to P naught into A star upon square root of T naught times, and here this entire term is nothing but a function of gamma comma R. Okay, now if you choose a particular calorically perfect gas, then for that particular gas gamma and R will be constant. Okay, gamma and R will become constant for a particular gas, and for a situation of a nozzle. So in case of nozzle, what we have? In case of a nozzle, we have somewhere here we are having occurrence of the normal shock wave. Okay, so it means that in case of a nozzle, basically I am not adding any heat from the surroundings, neither I am removing any heat. And this normal shock wave is also, though it is an irreversible process where actually entropy of the flow increases, but ultimately heat transfer across the normal shock wave is also zero, because we are not adding any heat or removing any heat from this place. So it means I can say that from inlet to outlet, my entire situation is nothing but adiabatic. Okay, so if I have adiabatic situation, we know that for adiabatic situation TO will be equal to TOE. So stagnation temperature at inlet will be equal to stagnation temperature at outlet. Even across the normal shock wave also stagnation temperature remains the same. So for this situation T naught will also be a constant parameter. Is this point clear? So as T naught will be a constant parameter, from here you can simply say that, and once your flow has choked, what I am saying is once normal shock wave will be only occurring when we have a choked flow situation, and once the flow has choked, then mass flow rate also becomes constant. Mass flow rate does not vary with the pressure. So for a choked flow situation, mass flow rate is also constant. So this is for choked flow situation. Okay, if this is the case, only parameter left with is P naught into A star. So I can say that P naught into A star will be equal to constant. This is an important point. Okay, so P naught into A star will become constant. Now what I can say that for a nozzle, so remember this point, P naught over here is reservoir pressure. So reservoir pressure, static and stagnation both will be same. Okay, so ultimately I am targeting it as nothing but a stagnation pressure. So this is a stagnation pressure of the reservoir. Okay, into A star equal to constant. Now I can say that for this type of flow, P naught into A star has to be equal to stagnation pressure at exit into area of exit. Is this one clear? Because this is stagnation pressure into area is becoming constant. So stagnation pressure of exit into area of exit has to be constant. Okay, so this is one important relation. Say this is relation number 1. Now let me calculate ratio of P exit into A exit. So now please make the difference. This is stagnation pressure and this is static pressure. So static pressure into AE divided by stagnation pressure at exit into area of exit. I want to calculate this ratio. Now what I can do, I can write in the denominator, because these two parameters are equal to P naught into A star. So I can write this as P naught into A star. So simply it is becoming PE by P naught into AE by A star is always known to us. Okay, so for a particular nozzle, because its throat area will be known, exit area will be known, and similarly in order to allow the flow through the nozzle, we have to maintain the pressure, okay, at reservoir and at exit. So PE by P naught will also be known to us. So as these two parameters are known to us, it means I can determine this complete ratio. And ultimately I also know that P naught by PE is nothing but equal to 1 plus gamma minus 1 by 2 into m square whole power gamma by gamma minus 1. And what is the formulation of AE by A star? AE by A star square is equal to, please tell me what is the relation, 1 by Mach number square times 2 by gamma plus 1 plus ME square, now because I am calculating AE by A star, whole power. Okay, so these two parameters are known to me. So what I can do now, I can actually calculate this ratio. So if I calculate this ratio, it will become PE by PO, PE by PO into AE by A star, and P by PO will become 1 plus gamma minus 1 by 2 m square. This also will be exit, m exit square whole power minus gamma by gamma minus 1. Okay, and this I can write 1 by me. Fine, this will be 1 by me because I have to take square root. So, and multiplied with 2 by gamma plus 1 into 1 plus gamma plus 1 by 2 times gamma minus 1. So 1 by 2 has come because of the square root. Okay, so now if you further simplify this equation, you can actually calculate the value of me. Okay, so by simplifying this relation, I can calculate the value of me. So if I calculate the value of me, it comes out to be me square is equal to minus 1 by gamma minus 1 plus square root of 1 by gamma minus 1 square plus 2 by gamma minus 1 into 2 by gamma plus 1 whole power gamma plus 1 by gamma minus 1 multiplied by PE into A star divided by POE into A star, POE stagnation pressure, okay, into PE by AE whole power 2. So this is something which I will be getting. Fine. Now this parameter POE A star by PE into AE. So this is the parameter. So this is known to us, and all the values gamma are also known to us. So it means that by knowing this parameter, I can predict the value of the exit Mach number. Okay, so I can predict the value of exit Mach number. So exit Mach number is now known to me. Okay, now let's see the situation. Say this is your shock wave, okay, and this is point O, this is point E, and this is point 1 and this is point 2. So here I will be having pressure POE and PE, and here say I have pressure P2 and PO2. Fine. Now similarly here I will be having pressure PO and PO1 over here. Okay. Now in the downstream, what is the situation? Downstream of the shock wave, I have complete isentropic flow situation. If I have isentropic flow situation, then I can say that PO2 will be nearly equal to POE. There will not be any change in the stagnation pressure. Similarly, upstream also I have the isentropic situation, so I can say that PO will be nearly equal to PO1. Okay. These 2 points are clear. So it means that I am knowing across a normal shock wave what is P01 and what is P0. These two values I am knowing across a normal shock wave. If I am knowing these two values across a shock wave, then by knowing the ratio of P01 by P02, I can calculate the Mach number which is at point number 1. We have normal shock relations. By using the normal shock relations, if I know stagnation pressures on upstream and downstream of the shock wave, by using the normal shock relation, I can calculate the value of Mach number at point M1. Okay. Now I know at M1 my flow has to be supersonic. Okay. Then only I will be having a normal shock wave. Okay. So flow has to be supersonic. Now I have this relation A by A star square equal to function of Mach number. This relation I am having, area Mach number relation. Now if I know the Mach number, then I can substitute this into this area Mach number relation, and from this, because I will be getting two solutions, one for subsonic, one for supersonic, so I can choose the supersonic solution to calculate the value of A by A star. If I have calculated the value of A by A star, it means I have now the location of the normal shock wave. Once you have the location of the normal shock wave, you can now easily solve as per the solution of problem number 2 to determine all other parameters. Is this point clear? So this is a deterministic approach. In this deterministic approach, actually what we can do, if we have the ratio of PE by PO and AE by A star, by just knowing these two parameters, what we can determine, actually we can determine the location of the normal shock wave. How? First we calculate the exit Mach number, and once exit Mach number is known, then we take the advantage of isentropic flow to predict the values of pressure across the normal shock wave. Once these two parameters are known, then using these I can calculate the Mach number using the normal shock relation at the upstream of the shock wave, and then I can substitute it back into the area Mach number relation to calculate the value of area at the occurrence of normal shock wave. Okay, and once this is estimated, then actually my whole problem is very simple, as we have discussed in the previous lecture. Is this one clear? So anyone is having any issue up to this point? Okay, so now this is all about nozzles. Now let's discuss the counterpart of the nozzles, which is called as a diffuser. Okay, so to understand a diffuser, what we will do, we will try to take different situations, and then we will understand why there is need of diffuser. So first let's understand what is the need of diffuser. And to understand this, what we will do, we will take the help of a wind tunnel. So what I want to do, I want to have a wind tunnel where I want to say analyze my some section, and this section I want to analyze actually for supersonic conditions. Okay, so what I have done, initially I have thought of a wind tunnel that I will not put any structure, I will just go for a nozzle. I will just go for a nozzle like this. So this is the exit of the nozzle. I have taken a nozzle, and let's consider that exit of the nozzle is nothing but at atmospheric pressure condition. So what you want to do, you want to do exit at high Mach number. So say here M exit, this has to give supersonic situation, but this exit has to be happen at atmospheric pressure condition. Okay, so that is the situation, say, which I have taken in hand. Ultimately I want to remove add the air to the ambient at 1 atmospheric condition, but if I want to place my test object here, that test object should face nothing but a supersonic Mach number. Okay, so my Mach number over here should be supersonic. Let's consider, so what we will do, we will try to compare some numbers for different situations. So what are these numbers? These should be based on some fixed criteria. So what I will do now, I will select that, say the Mach number which I want to maintain at the exit is 3. Okay, so 3 is the Mach number which I want to maintain at the exit. Okay, and now what I can do, I know nozzle, I know the throat area, AT, which will be equal to A star, because if the flow has to be supersonic over here, then at the throat I must have a sonic condition. So if I have a sonic condition over here, then area of throat has to be equal to A star. Okay, so AT is equal to A star over here. This exit Mach number is known to me, and now if all these parameters are known to me, I can actually calculate the ratio AE by A star. Okay, because Mach number is I have taken already fixed. So AE by A star will be the supersonic solution of area Mach number relation, and if you calculate that ratio, that comes out to be 4.23. Okay, so that ratio comes out to be 4.23. Now once this ratio is also known to me, I can actually predict the value of the pressure ratio I can predict. Okay, so if I calculate pressure ratio, P exit by PO for this situation comes out to be 36.7. So 36.7 is the pressure ratio for this. If 36.7 is the pressure ratio, it means that my stagnation pressure over here at the reservoir has to be equal to 36.67 into 1. So that will be equal to 36.7 atmosphere. So 36.7 times of atmospheric pressure has to be maintained at the inlet of the nozzle. If this much pressure is there, then only we will be able to achieve supersonic flow with Mach number equal to 3 at the exit. Okay, so it means this pressure ratio is huge. Okay, so ultimately here I want atmospheric, but the pressure over here which is required at the reservoir level, this is 36.7. So it means if you have to use a compressor for providing pressurized supply of air, that compressor has to compress the air from atmospheric pressure to 36.7 times of atmospheric. So this will be a huge energy consuming operation. Okay, now to avoid, to see the different possibilities, that what are the other possibilities we have, what I will do I will consider a diffuser section like this. Now what I have done, I have not done the direct exit, but here where nozzle is ending, from this point I have taken a horizontal constant cross section duct over here, and this duct is nothing but my test section. So now in this duct I want my Mach number to be 3. Okay, so here my exit, this is the exit of the nozzle, so this is given by point E. So my exit Mach number over here is equal to 3, and I am not concerned of pressure over here, but I am concerned of pressure at this point, that whenever it will be exiting into the ambient, then it should have atmospheric pressure. So say here my P infinity should be equal to, after the test section, my duct is actually supplying flow at 1 atmospheric pressure condition, and just over here I have Mach number of 3, and say here exit pressure is PE. Okay, and now when I will be doing this type of exit, ultimately what will happen, this is a constant area duct, so here I will be finding that I will have the presence of a normal shock wave. Okay, because if you are having a supersonic flow and then you have a corner, so here suddenly flow is creating corner. So here you will be having the formation of a normal shock wave. Okay, now this is say my point number 2 on the downstream of the shock wave, and on the upstream this is point number 1. So ultimately my P2 is equal to P infinity, which is equal to 1 atmospheric. Okay, now I know that at the upstream of the shock wave my Mach number will be equal to Me, because from this point to this point I don't have any mechanism to decrease the Mach number. So if I know this Mach number, if I know the exit pressure across this normal shock wave, I can predict the value of the upstream pressure. Is this one clear? So I know downstream pressure, I know Mach number at the upstream. So using the ratio of pressures across a normal shock wave, by knowing the upstream Mach number, I can predict the value of P1. And from PE to P1, because for a compressible flow situation we are considering inviscid flow, for inviscid flow there will not be any static pressure loss, so PE will be equal to P1, and that comes out to be for this situation as 0.097 atmospheric. Fine. Now what we have, now I know this exit pressure and I know this throat area. So these two parameters are known to me. Now if I have to calculate my pressure PO, so PO will be equal to PO by PE. This is E, this is O. So ratio of pressure between exit and reservoir multiplied with PE by P2 multiplied with P2 by PO2 and multiplied with P infinity. So what I have taken the combinations of the pressure so that I can eliminate all and then simply get the value of P naught. So here what will be happening now, what is PO by PE? So what I have done, whatever the nozzle was there in the previous case, I have same nozzle with same throat area. I have not made any modifications to the nozzle. The only modification I made is I have extended one duct. So if for previous nozzle pressure ratio was 36.7, for this nozzle also pressure ratio will be 36.7. So here first ratio PO by P6, because nozzle is remaining unchanged, only I am using an additional duct. So pressure ratio across the nozzle will remain the same, because Mach number also at the exit of the nozzle is the same. So PO by PE is 36.7. Then comes to PE by P2. Okay, so what is PE? Exit pressure, and P2 is this pressure. So here you can see P2 is equal to 1 atmospheric and PE is equal to 0.097 atmospheric. So if you calculate this ratio, you will be finding this ratio comes out to be 10.33. So it will be 1 divided by 10.33. 1 divided by 0.097 will be 10.33. So opposite of this is 1 by 1.10. Okay. Then we have next P2 by PO2. How to calculate P2 by PO2? Tell me. What will be P2 by PO2? Now, if you calculate P2 by PO2, so here you know the Mach number. Okay. You can, you have a normal shock wave. Across this normal shock wave, you can predict the Mach number at point 2. Downstream of the shock wave, you can predict the Mach number. If you can predict the Mach number, you can calculate the ratio of PO2 by P2 will be equal to 1 plus gamma minus 1 by 2 M2 square whole power gamma by gamma minus 1. So if you calculate this ratio comes out to be 1.17. Okay, so as this ratio is 1.17, so opposite of this will be 1 divided by 1.17. and ultimately P infinity is equal to 1. So from here, if you calculate this initial pressure PO, that comes out to be, from here PO comes out to be 3.0, sorry, 3.55 atm. No, I made a mistake over here. I even need not to calculate this. So what I can do, I can simply calculate the value of PO as equal to PO by PE times PE by P2. So now PE will be cancelling out, multiplied with P infinity, that P2 and P infinity will cancel out. Okay. So this first ratio was 36.7 and second ratio was 10.33 multiplied with 1. So from here, if you calculate, it comes out to be 3.55 atmosphere. Sorry, because I have only these pressures PE, P2, P infinity and PO. So with these pressures, I can actually obtain this expression. So over here, my PO now is, compare with previous case. Previously, how much pressure was needed? So it means if you just exit a nozzle directly into the ambient condition, you need a pressure of 36.7 atmospheric at the, but if you use a constant cross section, then and then you do the exit, then you are requiring a pressure of 3.55 atmosphere. There is a huge drop in the pressure. So this much huge drop in the pressure will lead to actually significant drop in our requirement of energy to maintain the supersonic flow situation. Okay, now let's little bit more advance in some slightly more modified design. What I will do now, I will take some nozzle like this, same nozzle, same constant cross section, but after the test section I will actually use a diverging duct, something like this. Okay, so here I have PO, this is the exit point E, here I have Mach number of 3 and pressure of P exit, and this is a constant area duct. So this is the point where I have normal shock wave. Okay, so it means this is point 1 and point 2, and after that I have once again a variable diverging duct. Okay, and from diverging duct, then here I am having exit at the ambient. So in this case, this is my P infinity equal to 180. Another important point is that here I have a normal shock wave. So on the downstream of the shock wave, I will be having a subsonic situation. So M2 will be less than 1. Okay, as M2 is less than 1 and then I am having a diverging duct, what ultimately will happen? This is a subsonic flow through a diverging section. So for subsonic flow through a diverging section, there will be further decrease in Mach number and I will be having here gain of pressure in the duct section. Okay, so at the infinity, if I see Mach number, that will be very small than 1, and this Mach number will be so small that I can assume that P naught infinity is nearly equal to P infinity. Is this point clear? So what I am saying is, after I have used a diverging section on the downstream of the shock wave, already my flow situation is subsonic. As flow is subsonic in a diverging duct, it will further lead to decrease in Mach number and increase in pressure. Okay, so that's why my Mach number at the exit will become very small, and because due to this very small Mach number, I can say that stagnation pressure and static pressure will become almost the same. Okay, up to this point, is it fine? Now here Mach number is 3. Now let's try to see the situation. So for the normal shock wave, I know now one parameter. First parameter is that PE is equal to P1. Pressure I am knowing at point 1. I am also knowing Mach number. M1 is equal to ME. So on the upstream of the shock wave, I also know Mach number. If I know the Mach number on the upstream, then I can predict the Mach number at the downstream. So if you calculate the Mach number, M2 is coming out to be 0.475. Okay, so our M2 comes out to be 0.475. Okay, now one important point, this P naught infinity is equal to 1 atmospheric. So I can say over here that P naught 2 will also be equal to 1 atmospheric. Okay, so if P naught infinity is 1 atmospheric, then P naught 2 will also be 1 atmospheric. Okay, now using this diverging duct relation, if you calculate pressure at point 2, pressure at point 2 comes out to be, Mach number is known at this point, and then P naught 2 is known. So now I can use the relation P naught 2 by P2 equal to function of M2. So M2 is known. I can calculate the value of P2 because P naught 2 is also known to me. So from here P2 will comes out to be 0.857 atmospheric. I have pressure known. If downstream pressure is known and upstream Mach number is known, I can calculate the value of P1 using the normal shock relation. If I calculate that, then my exit pressure comes out to be 0.083 atmospheric. This is the value of the exit pressure. Once you know the exit pressure, then you can now calculate PO. So what will be the value of PO now? So now PO will be PO by P exit multiplied by P exit by P2, because P exit and P2 are different now, multiplied by P2 by P naught 2 multiplied by P infinity, because P naught 2 and P infinity are same. Okay, so if you calculate this, first pressure ratio is known to us from the nozzle, 36.7. Second pressure ratio is across the normal shock wave, that is also known to us from the previous section. Third pressure ratio is P2 by P naught 2. This is also known to us. This is 1 by 1.17. And last pressure is, calculate the pressure. If you calculate the pressure, it comes out to be 3.04 atmosphere. So just using a diverging duct, pressure has further decreased from 3.55 to 3.04 atmospheric. Okay, so here you can see that another important aspect is, here pressure is 1 atmospheric, here this is this. So pressure ratio of P naught by P infinity over here is nothing but 3.04. One interesting observation is over here. If you calculate stagnation pressure ratio across the normal shock wave for this situation, you will be finding that stagnation pressure P naught 1 by P naught 2 for this normal shock wave is also equal to 3.04. So what I can say that the pressure ratio which is required across this entire test section, entire wind tunnel, this pressure ratio has to be equal to the stagnation pressure ratio across the normal shock wave for the given Mach number, because this is the Mach number at the upstream of the normal shock wave. This is one important observation. Okay, so it means that if you have a constant section and then you are using a diverging duct, whatever the normal shock wave will be forming, the total pressure ratio across that normal shock wave will become equal to that of the pressure required to maintain the desired Mach number. Okay, up to this point, is it clear? Now can you think of some more arrangement which can give you the supersonic condition without consuming any energy? Can you think of? That will not take any energy and will give you a supersonic flow. Okay, let me try. What I will do, I will take this type of constant section and then I will use a converging diverging section. Okay, here what will be happening? At this point I need exit Mach number ME, pressure will be PE, here pressure will be P naught. Then here pressure will be once again 1 atmospheric, P infinity. Okay, now I have two throats, one is this, one is this. Say this is my 81 and this is 82. What I can say that, I can say that I have a nozzle, okay, I have a nozzle which starts at 1 atmospheric pressure condition, gives me Mach number equal to 1 at the throat, then results in supersonic, isentropic supersonic flow, then gives me a Mach number, required Mach number at the exit, some pressure at the exit. Then here I have a supersonic situation. So in case of supersonic situation, if I decrease area, my Mach number will also decrease. I have selected this section such that once again at the second throat I am getting a Mach number of 1, and then after this I will be having a subsonic situation where there will be pressure recovery, and finally I will be able to reach 1 atmospheric condition and almost stagnant situation. So if you see, ideally here also I am having 1 atmospheric pressure condition, here I am having 1 atmospheric pressure condition. So pressure required for this section is, pressure ratio is 1. So it means no pressure is required at the inlet, or say no vacuum is required at the outlet to create the flow. So I can say that this type of combination of nozzle and diffuser is something which is a perpetual motion machine. You just place in the ambient, here also you have atmospheric, there also other end also you have atmospheric, and inside you will get supersonic situation. But is this true? Why it is not true? Why it is not true? Can you tell what is the reason why it is not true? Which energy? Yes, that is there. So it is a perpetual motion machine. But what I am saying is, will it be feasible? If it is not feasible, okay, this is also proven that it is not feasible. If you just place a wind tunnel, there will not be a supersonic flow inside it. Okay, so we need to provide some pressure here or some suction here in order to create the flow. Then the next question is, if it is not true, yeah, not practical, then why it is not practical? What are the reasons? Immediately one thing should come to your mind. Whenever we are doing compressible flow analysis, we are neglecting viscous force. So friction we have neglected. So first thing is that in reality, friction will come into action. So one is the action of the friction, which we have at the moment neglected for simplifying our analysis. Second important point is, we know that if I have a supersonic flow here I am having a supersonic flow, and then I am having a converging section. So if I have a supersonic flow and then I have a converging corner, what will happen? There will be formation of shock wave. Okay, so these two things which we have not accounted yet, we are considering of a idealized situation, but ideal situation will not be there. Okay, so one thing is there, friction will be there, and another important point is we will be having, because here we are having a concave corner, sharp concave corner, so here I will be having formation of shock waves. Okay, so what ultimately I will be finding, I will be finding, say, some oblique wave will start and then say go this at this point, another will start at this point and then go like this, then these will interact over here, slightly refract, and then this will lead to a chain of shock waves. Okay, and obviously if we are having the chain of shock waves, these will make flow, these will make flow non-isentropic, and then we will be having decrease in stagnation pressure. Okay, so we have to provide something to sustain the pressure over here. Fine. So friction and occurrence of the normal shock wave are the two important factors which actually controls over here nothing but the which controls over here the um, flow dynamics. This is the reason we are not able to obtain a perpetual motion machine for this particular situation. Okay, but still the situation which we have studied over here, this is of a normal shock wave. Okay, we know that across the normal shock wave pressure loss will be more, entropy increase will be more, and pressure loss will be more. In comparison to this, if I use the combination of number of oblique shock waves, and then if say at the exits there is some normal shock wave is also say present somewhere over here, then also the Mach number over here will be so small that this normal shock wave will not lead to, this will be nothing but a weak shock wave. Why? Because at this point if Mach number is 1, then immediately after this whatever the shock wave will be forming, that will be identical to nothing but a Mach wave. Okay, so as it will be identical to a Mach wave, and in earlier we are having combination of the oblique shock wave, so total pressure reduction in this combination of oblique and a weak normal shock wave will be less in comparison to pressure reduction in a single normal shock wave. That we have proven earlier also in some of the numerical problems I have discussed in the class. Okay, so this is the reason that generally for designing a wind tunnel we prefer this type of design. Okay, where we after the test section we use once again a converging diverging section which acts as diffuser over here. Okay, now ultimately we see that just at the downstream of this diffuser, say if my PD is pressure, that will be nearly equal to PD naught, P naught D. Okay, because here Mach number will become very small. So if Mach number is very small, flow is almost the stagnant, and then static and stagnant pressures become almost the same, and this has to be equal to P infinity. Okay, this has to be equal to P infinity. Now important point is here we have area 81, here area 82. So what will happen to these two areas? That is something which we have to actually determine, that what should be the relationship between the two. So 81 and 82, whether these should be same, different, or in what ratio their difference should be there. So that is something which we have to actually determine. Okay, before that one important point I want to tell you that in case of diffuser actually, so I have shown you first point is need of diffuser. So need of diffuser is very clear to us. Whatever the first situation we have selected, their pressure ratio was 36.7. Then when I have used the constant section, then 3.55. When diverging section, 3.04. When this type of situation, ideally it should be 1, but because of the losses there should be some pressure ratio. Okay, so what we are expecting that, because as I told you that if I use a normal shock wave, then pressure loss will be more, but if I use a oblique and normal shock wave, so pressure ratio will be less. So I am expecting that in this situation I will be having slightly less pressure ratio in comparison to what we have discussed for a normal shock and a diverging section, which was giving us for that particular situation the least pressure drop. Okay, least pressure ratio. So this is the need for diffuser, that it decreases the requirement of pressure to maintain supersonic flow. But another important aspect is when we are using the diffuser, then we also must quantify the efficiency of the diffuser. Okay, so for using a diffuser and defining its efficiency, a number of parameters are used, but one important aspect is that the combination of a normal shock wave and then a diverging duct is considered as an ideal diffuser combination. Okay, and the pressure ratio for this, so pressure ratio for this will be nothing but equal to the stagnation pressure ratio across this. So P naught 1 by P naught 2 at ME across this normal shock wave. Okay, so that is something which we have considered. So this is the ideal situation. If this is the ideal situation, so I can define efficiency of diffuser as, if I use any geometry which is other than that, then we can determine the efficiency of that particular geometry relative to this. So for example, if this is the geometry over here, my delivery pressure is PD and starting pressure is P naught, reservoir pressure. So I can say that delivery pressure by reservoir pressure ratio. Okay, and also this delivery I have to POD for actual divided by P naught 1 by P naught 2 at, for normal shock, so this has to be for normal shock at Mach number exit, ME. So this particular term is called as nothing but the efficiency of the diffuser. Now what are the different aspects related to efficiency of the diffuser, that I will take up in the next lecture. Okay.